Last time we met, we talked about shear stress in a beam, and that's what we call indirect shear. What was the equation that we used to compute that shear stress?
All right. No, sorry, it said negative VQ.
Ah, excellent. Negative VQ. So V is the shear from your shear diagram of that beam. Q is the geometric calculation. Right, it's the integral of y, or we write it as the summation of y bar prime a prime. I has to do with the cross section. That's your moment of inertia. And then T is the width, perpendicular to the load direction at the particular point where we're interested in. So that's our shear stress, and that's in units of force per unit area. But there's something called shear flow, very directly related to shear stress, but this is the expression in force per unit length. So little q is what we call the shear flow. That's our force per unit length. And one reason it's particularly important is because we use it to design our connections. In particular, when we have discrete connections. So maybe we have bolts or nails or shear studs. I'll draw a picture of a shear stud in a second. And these are located at certain intervals away from each other. Similarly, we could have spot welds. So maybe we have a 1-inch weld every 12 inches. And when we have these discrete repeating connectors, we need to know how much force is being transferred through each connector in order to know the size of those connectors. So the shear flow, Q, is computed by taking our shear stress and multiplying by the width, right? If we already know the shear force per unit area, we then multiply by that width that is perpendicular to the direction of the shear force, and that gives us a shear force per unit length. And then if you want to know the shear force in a particular connector, you would take your shear flow and multiply by the spacing. And that gives you the pounds of force. So for example, if we have a beam, so this is a metal I-joist with flanges on the top and the bottom. And very often those types of beams will act in a building and they will support a concrete slab floor. And the way that we connect them is with shear tabs. So we have these metal pieces that come up like this. They're welded to the top of the beam. And then they are embedded in the concrete. So the beam is already in place with these shear tabs at the time when we pour the concrete. So therefore they end up inside the concrete. And then the two have to act together. You've created a composite beam. So if we look at this from the side, we have our beam and our concrete slab, which now those have to act together as one continuous beam. And each of those shear studs is going to be carrying this force V.
And spacing is the space between each Each one of them?
Yeah. The spacing is this dimension here.
Would that be the same as just like a bolt pattern? Would you use the same?
Your question is regarding what type of bolt pattern?
So just like if you, I don't know.
Oh, if you, okay, I see what you're saying. If you're connecting two things with a series of bolts, yes, same mathematical concept, whether it's bolts or nails. If you have any type of connector along the length of a beam, this is how you're going to figure out the demand on a particular connector. And so mathematically, this is VQ over I, and then we would divide by B to get the shear stress, except we're going to turn around and multiply it by B to get the shear flow. So we can just omit the B entirely, and then times S for your spacing. And that negative sign is not necessarily important, but it will tell you the direction. But typically it's not going to matter the direction. It's going to have the same. Your shear stud or your bolt's going to have the same capacity whether you're shearing it, one direction or 180 degrees. The shear is going to flow through a thin-walled cross-section from one extremity to the other. All right, so it's going to go from one extremity to the other. And when I say thin-walled cross-section, I'm talking about like an I-beam. So we might have something like this, or we might have something like this, where the cross-section has a thin width. So what I'm not talking about is like a chunk of wood, a rectangular chunk of wood. Okay, so that's the opposite of a thin wall. So in a rectangular cross-section, we know that our shear flow is just going to be vertical if we have a vertical load acting on this beam. But what we're going to find out is that if we have a beam with downward loading, if it's a thin-walled cross-section, that shear is going to flow around. It's going to start on the top and make its way down to the extremities. If our loading were acting upward, we'd see the opposite. These arrows would be starting on the bottom, flowing to the top. And we can show that this is the case by taking a series of cuts. So remember how we initially showed that we had shear stress by taking a section cut that was, say, horizontal, and we had the normal stress acting on the cross-section on one side, and then a normal stress acting on the other side of that cross-section that were not equal and opposite because the moment was changing, therefore the normal stress was changing. And so to put it in equilibrium, we said that there had to be a stress in that horizontal direction on that section cut. And then by extension, because of our sum of our moments, we knew we had this vertical component here in the middle. So we've already kind of gone through getting this component, but you also could do the same analysis, say at each of these other sides. And what you're going to find is that similarly, in order for that to be in equilibrium, so if let's look at this one here, for example, actually let's look at the one that's easier to draw. This one. So if I look here, we have our normal stresses like this, and the other direction like that. And in order for this to be in equilibrium, the shear stress component is now going to be on this face like this.
This is all loaded on top, right? Like the two cross sections that have loaded on.
Yes, yes. And actually, I think I misspoke when I said that loading it upward would give you the opposite. The direction of these arrows is going to depend on whether it's experiencing positive or negative shear stress. So for example, if you have a beam with loading, so this is your beam and you have your loading, let's just say it's distributed loading. The shear diagram for that is going to look like this, right? And so part of it's going to be positive, part of it's going to be negative. So it just depends which portion of the beam we're looking at. So, but assuming that this, you get the arrow pointing kind of towards the right, then you're going to have an equal and opposite arrow on this face like that, which corresponds to this arrow here. And then you can do the same thing in all these other legs, and you find that it ends up having to be in this direction. You can see the same thing on that circular cross section if you take those cuts. And the other thing that you find is that the magnitude is changing as you go along. If you think about how we calculate this, remember Q is negative VQ over I. V is not changing, right? V is constant on the cross section. I is not changing, but Q is changing. So Q is Y bar prime A prime. When we're taking our section cuts and we're going a little bit farther and a little bit farther until we get to this midsection, Y bar is the same for all of that analysis. So this is our centroid. Y bar is always going to be measured to the center line of that flange, but your area is increasing. And would you agree that your area is increasing linearly as I move from right to left? Okay, so if you would agree with that, what that means is your shear stress is increasing linearly. So that's what your distribution of shear stress is going to look like. Over here we have this distribution, and then you see similar on the bottom and on the top. But of course, now when you are down here in this web, now not only is your area increasing as you move closer and closer to the neutral axis, but also Y bar prime is increasing. So that's how you end up with that parabolic shape. You're going to get, now this parabolic stress is not going to start at 0. In fact, it's going to start such that this stress in the web is equivalent to the stresses or the shear flow coming from the flanges. So this should, I believe, be double what these are. So then they'll add together as they go up. All of our calculations when we do this are with respect to the center line. What I mean by that is the shear flow is passing through the center of our cross section. So this, for example, is our wall. This then is our flange, and you can see that there's a little bit of overlap there in that corner, and that overlap is equivalent to the area that we're missing, right? So all the calculations that are done, we use these shaded areas as our areas as opposed to the actual cross section. So when we talk about calculating I or Q, it's always going to be with this width as opposed to the whole width, or with this height as opposed to the whole height. So we'll do an example right now that shows this. So let's try to get the stress distribution. On a rectangular cross section, and we'll get some dimensions. We'll say that it's 3 inches and 1 inch, and that's the same top and bottom. And in this direction, it's 2 inches and 1 inch, same left and right. And we're acting on it with a 10 kilonewton, or sorry, 10 kip force. And we want our shear distribution. The first thing I want to do is I already have V, so this 10 kip presumably comes from a shear diagram, but now I want to get I. How would you like to get I? Do you want to use the parallel axis theorem and the different pieces, or would you like to do one? Yeah, is that what you like?
That's what I thought.
Okay, I'm fine with that. So we have 1/12. Now our width is going to go all the way to the outside. That's going to be 6 inches. But our height is now going to be to the center lines of the top and the bottom. So that's only going to be 7 inches cubed. And then we'll subtract 1/12 times 4 inches times no, and it's kind of hard to show with this method. So the areas that we're looking at is that whole area, this whole area, and then we want that. Can you do this math and see what you get? I want to see what you get. Because if we do it separately, which is the way that we all, or most of us don't prefer to do it, it's a little bit easier to show. So on the other method, for the blue, the sides, we have the 1/12 times the width would be 2 of them. So there's 2 of them times 1 inch. And then the height is only the 7 inches cubed. And then plus, let's see, there's 2 of these, the top and the bottom. And they have 1/12 times B. Now the width is going to be 5 inches instead of 6, because we're only measuring to the center line. But we're going to measure the entire height, which is 1. And that is cubed, so plus your 80 squared. Your area is 5 inches times 1 inch. And now the measurement is 3.5 inches squared. So let's calculate those both and see what we get.
So this one is 99.
Okay, that number is not right. What's the second one?
Where does Q supposed to be on the top one?
Is that what you're asking for?
No, sorry, so in the first.
Ah, you're asking about this number? That should be here, right? Oh, did you put it on the, where'd you put it?
Actually, no, I did.
You put it right, okay. Yeah.
Why is that 7?
Because we're measuring from center to center.
Oh, center. All right.
Yeah.
Got 180.
Okay, that's what we want, 180. I'm curious though, if we make this 8, do we get 180 or something close to it? Because I think that would be the norm. That would be the normal, right? 112.
184.
184. So 184, that would be your typical I, right? You would agree that that equation is just your normal I calculation. So it's not going to make a big difference, but it does slightly decrease your capacity when we do it like this. And I guess I wouldn't use that method where you take one and subtract the other for this, just because it becomes difficult with the way that you're trying to adjust the dimensions. Okay, so now we have I. We're going to need to calculate Q at a few different locations to get our distribution. I would say that probably these 3 points, we'll say that's A, B, and C, will be enough. So at A, we know that Q is 0, because that's where our flow is going to start, right? So our area at that point, we could say, is 0. There's no area that we've considered yet. And then as we go out from that point, our area gets bigger. So if we're looking at point B, we're now looking at this area. We started at point A, and then we extend on both sides until we get to point B. And so Q for point B is equal to, see, y bar A prime. Y bar is going to be 3.5. That's the height from the neutral axis to the center of that top flange. The area is now the thickness, which is 1 inch, multiplied by this distance from center line to center line. So we're not going all the way to the extremity. We're going center line to center line, and that gives us 5 inches. So it's 5 times 3.5, which is 17.5.
Oh, so we don't just multiply by the distance from A. We have to account for area on both sides of it.
Yes and no. We're going to divide by 2 at some point.
Oh.
So if you didn't account for the whole area, you wouldn't divide by 2. Okay, so here we have the 17.5 inches cubed. And then when we calculate Q, we have the 10 kip for V. We have 17.5 inches cubed. We have 180 inches to the 4th for I. And then we divide by 2 because this shear force is being transferred at 2 different locations, at point B and then the mirror image of point B on the other side. And that should give us 0.487 kips per inch. And we know because we're traveling along a horizontal member it's going to be a linear distribution. Okay, and then when we get to the sides, we know it's going to be parabolic, and it's going to start at the same value. So now it's, when we had the I-beam, the two flanges were adding together to go into the web, but here we just have the one side continuously flowing into the next, and so these are just going to be equivalent. But we want to know that maximum value of Q. So at point C, we want to know Q. So now we have the sides. We have two sides. And the Y bar for those, we're going to say is half of the 3.5. So once again, these sides are being measured from the neutral axis just to the center line of that top piece. So then the centroid of that would be at 1/2 times 3.5. And then that gets multiplied by the area, which is the 1-inch thickness times 3.5. But we also have the top piece, which has a Y bar distance of 3.5 and an area of 5 inches times 1 inch. And so that total ends up being 29.75 inches cubed. And then Q is 10 times the 29.75 inches cubed over 180 inches to the 4th. Yes, thank you. Still have to divide by 2 because we're splitting that along the two sides. And so that equals 0.828 kips per inch. So here is, oops, 0.828 and 0.828. Questions?
Just the Y bar for the QC, the first one, the first part. I'm not sure how we get to 3.5.
Okay. So our neutral axis is here. 3.5 is the distance to the center line of that piece. This distance here is 3.5. And that's the height of our area that we're looking at, right? This side here has a height of 3.5. Therefore, the centroid of it has to be half of that. Good question. Anything else? Okay. All right, so there's another phenomenon that happens when we're looking at thin-walled members, and that's when we have open members. So an open thin-walled cross-section is one that does not close. So let's see, a couple examples are C-shaped, could even be more like this. Okay. Anything that doesn't close on itself is what we consider an open thin-walled cross-section. And these can bend, or they'll bend, but they also are susceptible to twisting when you put a transverse load on them. And so in order to avoid them twisting, you need to make sure that that load passes through what we call a shear center. And it doesn't matter at what angle it passes through. It doesn't necessarily have to be vertical or horizontal or parallel to any plane of symmetry. It can be any angle of inclination of the load. As long as it's passing through your shear center, then you will not have rotation. So to look at what happens, when we have a symmetric cross-section, this is not necessarily a problem. So if we have a symmetric cross-section, and we apply load through the centroid. So this is our applied load, and our unit shear looks like this. And you notice that the unit shear is symmetric, both in direction and magnitude. And so this will be in equilibrium. There won't be anything causing it to rotate. But that's not the case when we place a load through the centroid of, say, a C shape. So that would be your centroid location. And if I place a load through it, now the distributed shear looks like this. And what happens is if you take the moment, you could take it about the centroid, or because the sum of the moment should be the same about any point, I could take it about an easier. Now, if I'm taking the moment created by the shear stress in this member, don't consider the force applied to it. I'm just looking at what is happening within the member. We have this vertical distribution of shear, which is going through that point I'm taking the moment about, so that doesn't create any moment. We have these two flanges that are equal magnitudes but in opposite directions. That's going to create a couple, which is going to create moment. So this is not an equilibrium. And you will end up seeing rotation. But we can avoid that rotation if instead we place the load through what we call our shear center, which is going to be located off here to the left. And the way that we locate our shear center is by integrating our shear flow to figure out the amount of moment. And then we place our load P, our applied point load, such that the moment is the same from that point load and from the shear flowing arrows that we've drawn. So you know it's going to be on the left because these arrows that we've drawn create counterclockwise rotation, which is what we want to see. We want a counterclockwise, I shouldn't say rotation, they cause counterclockwise moment, and putting the P over to the left also gives us that counterclockwise moment. So we know that the moment, if we call this E, the moment PE, where E is measured to that vertical member, center line of that vertical member, has to be equal to the force in the flange, which we got by integrating the Q. Right? Q was a linear function, and so we're going to integrate that over the flange, and we multiply it by D, where D is that center line to center line distance between the two flanges. So once we find E, so what we're solving for is this E value. Now we know that's the point through which we can apply loading, and it won't cause any rotation in the beam.
So the F was for the flange was the one in the flange, the going sideways, right? Not the one going perpendicular to it.
Yeah, the F flange, that's these arrows that are circled in blue, those horizontal arrows. So you might be asking yourself, how do we apply a load that's not touching the member? A lot of times what they do is they put a little angle on the back here, and then the load gets applied on that angle. Yes?
What is F flange?
F flange is the integral of this load Q. So say Q goes from 0 to 100, and this is, say, pounds per inch. We're integrating that force per unit length over that length to get a total force. Other questions? Then I have a example / ICA. I want you to do the first part as an in-class assignment, the first part being getting the Q distribution, and then we'll come back together as a class and we will calculate the shear center. So what you need to know is I have a beam. With a point load of 100 pounds. And the cross section is a C shape. All of these members have the same thickness. Thickness is 1/2 inch. And the dimension from the center line to here is B. B is 3 1/4 inches. And then the center line to center line dimension vertically is 10 1/2 inches. So get that distribution of Q in, you can get it in the web and the flange, but why don't you start with the flange, because that's what we're going to need in order to calculate our shear center. Go ahead and take a look at what you've done. Did you calculate I?
48. We got 93.
Let's see, what did you do?
So we had 2 flanges. So I just multiplied 1/12 by 2, so it's 1/6. And then I used 3.25 times 0.5 cubed
Okay,
for the area.
that makes sense to me.
For that. Yeah. And I had 1/12 times 0.5 times 10.5 cubed.
Yeah,
And the 80 squared, so 3.25 times 0.5.
this is going to be 2 of them as well, right?
280 squares. Yeah.
Okay,
I did not do that. So
so 2 times 3.2.
3.25 times 0.5 times 5.25 squared.
Okay, is that what you did over there?
No, we used the 80 squared.
Okay.
Where's that 80 squared from?
So-
Paralyzed.
But why do we need it? Okay, so the 80 squared, in the end, what I should tell us is a measure of the shape's resistance to bending about this axis. And that axis is located at the centroid. When we look at a particular component of the cross section, for example, if we're just looking at this shape here, the 1/12 BH cubed mathematically gives you its resistance to bending about this axis. But if you want it about that axis, the way that you get that quantity is with the plus 80 squared. Okay. So can we get a revised number?
137.88.
Okay. Good. Are we all in agreement that this looks like a good I value? All right, V, how'd you get V?
It's from the shear diagram.
Perfect. What does your shear diagram look like?
Go up, straight line, down 100, straight line.
Good. And these are each 50?
Yeah.
Perfect. So V is 50. No matter where we're looking in this beam, it'll just be opposite directions. Okay, now we need Q, big Q, and we decided that we were going to calculate it so that we so that it pertained to this point here. This is where we want to calculate little q. So big Q then is only going to include that shaded area. That will be our A prime. Our Y prime is the measurement. Y bar prime is the measurement from the centroid of that flange to the neutral axis. So that dimension is going to be half of 10.5. So 10.5 divided by 2. And now times the area. Now that area is the thickness, which is 1/2, times B, which is 3 1/4. That's going to give us some value of Q. And we could use this to get little q. And then what do you get for that big Q? 8.52? 3? 8.53 inches cubed. Okay, so little q then equals 50 pounds times 8.53 inches cubed over 137.88 inches to the fourth. And what do we get? Okay, pounds per inch. So now if we're integrating, we know that P times E has to equal the force in that flange. So the force in that flange is that integral, right? It's going to be 1/2 3.09 pounds per inch times 3.25 inches. And now we need to multiply by D, because that's the distance between those two lines of action. And P I can divide each side. P is 50. All right, so what do we get for E? Question.
Why don't we have a Q value for like the vertical part?
Why don't we?
Yeah.
We didn't calculate it because it's not necessary to get our shear center, but we could. You could, and this value here will start off being equivalent. So this value would be 3.09, but then you could calculate big Q at this point here and get this little q. But remember that when we were calculating our shear center, we were taking the moment about this line in our equation to get E so that we could disregard it. Do you have a value for E?
1.06.
Good, 1.06 inches. Perfect. That means that if we come over here 1.06 inches. That's where we want to apply our force P. Cool.
Yeah, just for the, when you calculated E, and then, for the, you said it's the integral, F flanges, how did you get that? Like the half and the 3.25?
So the distribution is triangular, so I just took the area of that triangle, 1/2 times the base times height. But here's what you could do. Instead of calculating Q at a particular location, we could make this X, where X starts at 0 on the extremity and then moves inward, right? And at any point, you would have Q, because Y bar stays the same. And then 1/2 is the thickness, that's always the same. And the only thing changing is how far in you're coming. So this then becomes a function of X. So then you could calculate this Q truly as the integral. So, all right, sorry. No, Q would be a function. What am I doing? Q would be a function of X, right? Because this function of X would become that function of X. And then E. E would be, instead of doing this here, E would be the integral of Q dx. Okay, the integral of Q dx from 0 to 3.25. That would give you your force. I don't understand why that does that. Okay, integral of Q dx, that gives you your force, and then you would multiply by the height.
So in there, when you did it without an equation, it was only 3.25, that's the B distance, and then divided by 2, or multiplied by 1.
Other questions?